Welcome to chapter 5 of number theory. In this chapter we are going to see three additional topics. One is Gaussian integers, then Pythagoras triples, then the last topic is the Pell's equation. In this module we are going to define and introduce various properties of Gaussian integers. In particular, we are going to extend the notion of prime numbers, composite numbers and related results of integers to Gaussian integers. In chapter 5, we will see three additional topics. The first one is in this module 1, we are going to discuss the set of Gaussian integers. The objectives of this module are, we are going to define what are Gaussian integers and we will see various properties of Gaussian integers, primes in Gaussian integers, how primes in Z going to split in Gaussian integers. So, definition of Gaussian integers. The set of Gaussian integers is denoted by Z of I, where I square equal to minus 1. It is defined as Z of I is equal to x plus Iy such that x comma y are integers. So, the Gaussian integers behaves like look like complex numbers. In the complex numbers x and y are real numbers, whereas in the Gaussian integers this x and y are integers. So, observe that Z of I, the elements in Z of I are x plus y, hence look like similar to set of complex numbers, but x y belongs to Z. Hence it is a proper subset of complex numbers which contains Z, as if I take y is equal to 0 and if you keep varying x value, then Z of I contains all the integers. Addition and multiplication Z of I is defined as, addition is defined as a plus ib plus c plus id is equal to a plus c plus I times b plus d, and multiplication is defined as a plus ib into c plus id, which is equal to ac minus bd plus ad plus bc into I. Here we are using that I square equal to minus 1. Then if we do ordinary multiplication, then we will get that one. A plus ib into c plus id is equal to ac minus bd plus ad plus bc into I. This multiplication is same as complex numbers. It is because we are already noticed that Z of I is subset of proper subset of complex numbers. It is clear that Z of I is closed with respect to addition and multiplication. Moreover, these operations satisfy associative laws, distributive laws and so on. It is because they are already true in complex numbers, so they will true in Z of I as well. We will also define the following to take care of size of an element, that is called norm of a Gaussian integer. It is like a modulus of an integer. In the for integers, modulus will give the positive integer except 0. So, similarly here we are defining norm of an integer which takes a Gaussian integer to an integer. So, it is defined as if alpha is equal to a plus ib belongs to Z of I, then norm of alpha denoted n of alpha is defined as n of alpha equal to a plus ib into a minus ib. It is like a conjugation of a plus ib. So, this is equal to, by multiplication of Gaussian integers, which is equal to a square plus b square. For example, norm of 3 plus I4 is equal to 25, and it is because 3 square plus 4 square is 25, and norm of 1, that is 1 plus I into 0, or norm of minus 1, that is minus 1 plus I into 0, or norm of I, that is 0 plus I, or norm of minus I, that is 0 plus 1 into minus 1 into I. All these norms are equal to 1. So, and one of the interesting property of this norm is that norm is multiplicative. That is, for alpha comma beta belongs to Z of I, then norm of alpha into beta is equal to norm of alpha into norm of beta. So, we are going to prove this. So, alpha is equal to a plus ib and beta is equal to c plus id, then norm of alpha by definition is a square plus b square, and norm of beta is c square plus d square. So, norm of alpha into norm of beta, which is equal to a square plus b square into c square plus d square, okay, which is equal to ac square plus bd square plus ad square plus bc square. So, which is again going to be rewritten as, just what we are doing here is that I am subtracting 2 ABCD and adding 2 ABCD. So, by arranging in such a way that AC square minus 2 ABCD plus BD square plus AD square plus 2 ABCD plus BC square, we can see that the first 3 terms comes out to be AC minus BD whole square, and last 3 terms turns out to be AD plus BC whole square. So, we know that A plus IB into C minus ID equal to AC minus BD plus I into AD plus BC. So, it is exactly the norm of alpha times beta. So, this is one of the interesting property of norm, that is norm is multiplicative, that is norm of alpha into beta equal to norm of alpha into norm of beta. So, we saw that in arithmetic functions also the multiplicative property is similar to this. There we required that GCD of AB is 1, but here there is no restriction. Now, we are going to look at units of Gaussian integers. First, what are units? Units means those elements which have multiplicative inverse. That means, for example, if you look at a set of integers, the only integers which have inverse are 1 and minus 1. It is because 1 into 1 equal to 1 and minus 1 into minus 1 is equal to 1, whereas for all other Gaussian integers, all other integers, for example, let us take 3. 3 into how much is equal to 1, that is 1 by 3. 1 by 3 is not an integer. So, 3 does not have an inverse. So, similarly here in the Gaussian integers, what are the units, what are the invertible elements? An element a plus ib belongs to Zi is called an unit if you are able to find out another Gaussian integer x plus iy belongs to Z of I, such that a plus ib into x plus iy is equal to 1. That is, for example, 1 minus 1 I minus I are units in Z of I. They are easy to see, it is because 1 into 1 is 1, minus 1 into minus 1 is 1, I into minus I is 1, minus I into I is equal to 1. So, clearly 1 minus 1 I minus I are units in Z of I. That means, in the number of invertible elements in Gaussian integers are more than the invertible elements in Z. Those which are invertible in Z are already invertible here, that is they are 1 and minus 1. So, in particular we are going to show that the only units in Z of I are these only, that is an element alpha belongs to Z of I is unit if and only if alpha belongs to 1 minus 1 or I minus I. That means, Gaussian integers contains only 4 units or 4 invertible elements. Clearly 1 minus 1 I and minus I are units in Z of I. Now, so conversely let us take alpha equal to a plus ib be a unit in Z of I. Then by definition there exists x plus iy belongs to Z of I such that a plus ib into x plus iy is equal to 1. So, if you multiply, if you expand it, that is by previous result. So, norm of 1 is equal to 1. So, norm of 1 is equal to norm of a plus ib into x plus iy, but norm is multiplicative, that is what we saw in the theorem 3. So, norm is multiplicative. So, this is equal to n of a plus ib into norm of x plus iy, but norm of a plus ib is a square plus b square, norm of x plus iy is x square plus y square. So, a square plus b square into x square plus y square is equal to 1. So, consequently a square plus b square, since a square is a positive, b square is positive, a square plus b square is positive, x square plus y square is positive. So, a square plus b square has to be 1 because a and b are integers. Thus, we have choices like a is equal to plus or minus 1 and b equal to 0, or A equal to 0 and B is equal to plus or minus I. So, consequently, the possible choices for A plus IB or A plus IB belongs to 1, minus 1, I and minus I. So, what we proved is the only units of Gaussian integers are 1, minus 1, I and minus I. Now, we look at the division in Gaussian integers. It is like usual division in integers. See, here one has to understand that we defined till now all the different notions in set of integers. Now, we are looking, is it possible to extend these results to other set of numbers. So, this is one example. It is difficult to give different examples. In this course, we are giving one example, that is set of Gaussian integers, how the results of integers can be extended to Gaussian integers. So, division in Z of I, let alpha comma beta belongs to Z of I, then alpha is set to divide beta if there exists a gamma belongs to Z of I such that beta is equal to alpha into gamma. It is similar to as we defined in the set of integers. So, one of the important result in the division of integers is fix C belongs to Z and alpha equal to A plus IB belongs to Z of I, then C divides alpha in Z of I if and only if C divides A and C divides B in Z. That is, we are looking that an integer is going to divide a Gaussian integer if and only if it divides both the parts, that is real part or imaginary part, means real here in both are real part, imaginary parts are also integers. That is why we are looking C divides A as well as C divides B in Z actually. So, the proof goes like this, since it is an if and only if condition, we are assuming that if C divides A and C divides B, then it is clear that C divides A plus IB also, that is it is because C divides A means A is equal to C into some x and C divides B means B is equal to C into y. So, if you substitute A and B values in A plus IB, then A plus IB is equal to x is C plus I into yc. So, I can take C common. So, C divides A plus IB. Conversely, if C divides A plus IB, then there exists D plus IE such that A plus IB is equal to C times D plus IE, which is equivalently, if you compare the parts, real and imaginary parts, equal to C into D, B is equal to C into E, or equivalently C divides A as well as C divides B. Hence, we proved the required part. So, now we see that how an integer divides a Gaussian integer. Now, we are going to see how when a Gaussian integer divides another integer, in that case what are the possible consequences. So, the theorem says that if alpha comma beta are Gaussian integers, if beta divides alpha in the set of Gaussian integers, then norm of beta has to divide norm of alpha. Note that norm of beta and norm of alpha are positive integers. So, beta divides alpha in the Gaussian integers, then norm of beta divides norm of alpha in integers. So, this is only one direction. So, since beta divides alpha, so by definition there exists gamma such that alpha is equal to beta into gamma. Hence, by previous result, that is norm is a multiplicative. So, norm of alpha equal to norm of beta into gamma, which is equal to norm of beta into norm of gamma. Thus, we have norm of beta divides norm of gamma. It is because we have norm of alpha as an integer. So, norm of alpha equal to norm of beta into norm of gamma. So, norm of beta divides norm of gamma is, but clearly converse is not true. So, one can see many examples. One of the example is if you take alpha equal to 14 plus 3i and beta equal to 4 plus 5i, then norm of alpha equal to 205, that is equal to 41 into 5, and norm of beta equal to 41. So, 41 norm of beta divides norm of alpha, but 4 plus 5i does not divide 14 plus 3i. It is because if you consider alpha by beta, that is 14 plus 3i by 4 plus 5i, if you take the conjugation and multiply 14 plus 3i into 4 minus 5i by 4 plus 5 into 4 minus 5i, that is 71 minus 58i by 41. But we know that C divides A plus IB if and only if C divides both A as well as B, that result we proved earlier. Here 41 does not divide 71 as well as 41 does not divide 58. So, this 71 minus 58 into I by 41 does not belongs to Z of I. So, converse of above theorem is not true. Another corollary to this is, if alpha belongs to Z of I, then n of alpha, that is norm of alpha, is even if and only if 1 plus I divides alpha in Z of I. So, it is only related to 1 plus I only. So, it gives a characterization that n of 1 plus I divides another Gaussian integer if and only if n of alpha is even. So, for that observe that norm of 1 plus I itself is equal to 2. If 1 plus I divides alpha in Z of I, then by previous result we have that 2 is equal to norm of 1 plus I that divides norm of alpha. So, 2 has to divide norm of alpha. So, norm of alpha is even. So, that direction is easy to see. Conversely, if alpha is equal to A plus IB belongs to Z of I such that norm of alpha equal to A square plus B square is even, then since A square plus B square is even, that means that A square plus B square is congruent to 0 mod 2, or equivalently A and B have the same parity. It is because if A is even and B is odd, then A square plus B square is not going to 0 mod 2. So, that is both A and B are even or both A and B are odd. Therefore, one can take, we take m is equal to A plus B by 2 and n is equal to A minus B by 2, then m comma n belongs to Z. It is because both A and B are even or both A and B are odd. So, A plus B by 2 is an integer, A minus B by 2 is an integer, that is why m and n are belongs to Z. And we see that m minus in into 1 plus I, which is equal to, by definition of multiplication of Gaussian integers, which is equal to m plus n into I times m minus n. So, which is equal to A plus IB itself. So, that means that what we have here is m minus in into 1 plus I is equal to A plus IB. That means that 1 plus I divides A plus IB, which is alpha. So, we proved the converse part as well. Now, we are going to define another important concept in Gaussian integers, that is what we call associates. So, before defining prime and composite Gaussian integers, we define the following. So, if alpha and beta belongs to Z of I, then alpha is said to be an associate of beta if there exists a unit u in Z of I such that alpha equal to u into beta. We have actually concept of associates in integers also. As you know, in integers the only units are 1 and minus 1. So, 5 is associate to 5 or minus 5. In general, any integer n is associate to n or minus n, whereas in Gaussian integers alpha is associate to beta if alpha is equal to u into beta, but we know that the units in Z of I are u value may be 1 or minus 1 or I or minus I. So, or equivalently we have that alpha equal to plus or minus beta or alpha equal to plus or minus I beta. So, each element is have 4 associates in the ring of Gaussian integers. Observe that the associates of A plus IB now are minus times of A plus IB, that is minus A minus IB, or I times A plus IB, that is minus B plus IA, or minus I times A plus IB, that is equal to B minus IA, and A plus IB itself is associated to A plus IB. So, 4 associates we are given for arbitrary Gaussian integer A plus IB. Further, if alpha and beta are associates, then it is easy to see that n of alpha equal to n of beta. It is because n of alpha, norm of alpha equal to norm of u into beta, but that is norm is a multiplicative. So, norm of u into norm of beta, but norm of u equal to 1 since u is unit. So, norm of alpha equal to norm of beta, but converse is not true. So, one can check that one easily, that is there exists beta belongs to z of I such that norm of alpha equal to norm of beta, but alpha is not an associate of beta. For example, norm of 2 plus 9i is equal to 85, that is also equal to norm of 6 plus 7i, but neither of them is unit or multiple of the other. So, though norms are equal, but they are not units. Also observe that for each alpha belongs to z of I, with norm of alpha is greater than 1, the numbers plus or minus 1, plus or minus I, plus or minus alpha and plus or minus I alpha divide alpha in z of I. Hence, for each alpha belongs to z of I has at least 8 divisors in z of I. These divisors are called trivial factors or divisors of alpha in z of I. Any other factor is called non-trivial factor. For example, whereas in the integers, every integer has at least 4 divisors, trivial divisors, that is 1 minus 1 and n minus n, whereas here every Gaussian integer has at least 8 divisors. Furthermore, if beta divides alpha in z of I, then n of alpha equal to n of beta, then beta is associate of alpha in z of I. That means, here we are asking two conditions. One is beta divides alpha as well as norm of alpha equal to norm of beta. Consequently, if norm of alpha is greater than 1, beta is a non-trivial factor of alpha in z of I, then 1 is less than norm of beta is less than norm of alpha. We defined addition, multiplication and division of Gaussian integers. Gaussian integers behaves like ordinary integers. So, the results like fundamental theorem of arithmetic, division algorithm, Bezoart's identity, etc. are applicable for Gaussian integers as well. And further we saw that the only units in the integers, now because of Gaussian integers and integer two different sets, so now onwards we will going to say that integers as rational integers. So, in the rational integers the only units are 1 and minus 1, whereas in the Gaussian integers we have 4 units, that is 1, minus 1, I and minus I. And also in order to give some bringing some Gaussian integers to integers, we define the notion of norm of a Gaussian integers. Now we are going to see further properties, that is what are the primes in Gaussian integers, what are the composite numbers in Gaussian integers and so on. Now we are going to define primes and composite numbers in Gaussian integers. The definition: let alpha belong to z of I with norm of alpha is greater than 1, then alpha is said to be Gaussian prime if alpha has only trivial factors, otherwise alpha is called a Gaussian composite. The definition is similar to set of integers or rational integers. There also we observed that in the definition of prime or a composite we assumed that the integer greater than 1. Here we are assuming norm of alpha is greater than 1. So, obviously when norm of alpha equal to 1, that is the units, units are neither prime nor composite. So, in order to have a Gaussian prime or Gaussian composite, the norm of Gaussian integer should be greater than 1. So, let P be a prime in Z, then P is called a rational prime. To distinguish between primes between Gaussian primes and ordinary primes, now onwards the primes in Z are called rational primes. So, for example, if you take 2 is a prime, but prime integer as an integer, but as a Gaussian integer it is no longer a prime. It is because 2 is equal to 1 plus I into 1 minus I. Similarly, 5 is equal to 2 plus I into 2 minus I. So, 2 and 5 are have non-trivial factors in Z of I. Thus, 2 and 5 are not primes in Z of I. It is because it has a factor. First, norm of alpha is greater than 1, norm of 2 is greater than 1 and it has factors 1 plus I and 1 minus I. And we are going to look at some properties of Gaussian primes. Let P be a rational prime and pi belongs to Z of I with norm of pi equal to prime, a rational prime P, then pi is a Gaussian prime. So, it is one of the important result that whenever norm of a Gaussian integer is a rational prime, that is a prime as an integer, then pi is a Gaussian prime. So, let us assume that let pi is equal to gamma into delta for some gamma delta belongs to Z of I, then P is equal to norm of pi which is equal to norm of gamma into delta which is equal to norm of gamma into norm of delta, as norm of gamma and norm of delta belongs to Z and P is a prime in Z. So, at least one of norm of gamma or norm of delta is 1, or equivalently gamma or delta is a unit in Z of I. So, that means if you write prime pi as gamma into delta, then one of them is a unit. So, that is saying that pi is a prime element in Z of I. Every prime in Z of I divides exactly one rational prime. It is another interesting property of primes in Z of I. The proof goes like this: let P be a Gaussian prime such that pi divides two distinct rational primes, say P and Q. So, pi divides MP plus NQ for every m comma n belongs to Z, but GCD of P comma Q equal to 1, hence there exists x comma y belongs to Z such that Px plus Qy is equal to 1. This is from Beezer's identity. Thus, pi divides Px plus Qy which is equal to 1, a contradiction. So, we proved that pi divides exactly 1 prime. So, now we are going to find out all primes which divide 2. We already observed that 2 is no longer a prime in Z of I. So, now we are going to see what are the primes which divide 2. Note that 2 is not prime. So, and 2 is equal to 1 plus I into 1 minus I, as 1 plus I is as a non-trivial factor for 2. So, let x plus iy be a prime dividing 2, then there exists a plus ib in Z of I such that x plus iy into a plus ib is equal to 2. Taking norm on both sides, we will get x square plus y square into a square plus b square is equal to 4. So, either x square plus y square equal to 1 or x square plus y square equal to 2 or x square plus y square equal to 4. So, out of these three, one has to happen. The condition that x square plus y square equal to 1 implies that x plus iy is a unit. So, the condition x square plus y square equal to 4 implies that a square plus b square equal to 1, hence a plus ib is a unit. Thus, x plus iy is an associate of 2. Now, consider that x square plus y square equal to 2 in Z. Then it has that x equal to plus or minus 1 and y equal to plus or minus 1 as only solutions, but the numbers 1 plus I, minus of 1 plus I into 1 plus I and 1 minus I or minus 1 plus I which come from the solution of x square plus y square equal to Z are associates in Z of I. Thus, 1 plus I and its associates are the only primes in Z of I which divide 2. So, we are able to find out all the primes which divide 2. Now, let P be a rational prime, then phi factors in Z of I as follows. Now, we are going to give that what happens to the primes in Z, how they behave in Z of I. There are three possibilities. This prime is no longer a prime in Z of I, it is going to split, or sometimes it is a square of some other number, or it will not split further. That means this is a prime in Z of I as well. So, that is if P is equal to 2, it is a prime in Z, but 2 is equal to minus I times 1 plus I whole square, and norm of 1 plus I is equal to 2 as well. So, here 2 is a square, it is not a square free in Gaussian integers. So, another thing is, if P is congruent to 3 mod 4, then P is a Gaussian prime also, that is all the primes which are of the form 3 plus 3 mod 4 are again primes in are Gaussian primes as well. In this case, norm of P is equal to P square, and when P is congruent to 1 mod 4, then it is possible to write P as A plus IB into A minus IB. Moreover, A plus IB and A minus IB are non-associate primes, with norm of A plus IB is equal to norm of A minus IB, which is equal to A square plus B square, which is equal to P. Further, A plus IB and A minus IB are unique up to associates. So, we are going to give the proof. The first part can be proved easily. For the second part, let P is congruent to 3 mod 4. Suppose there exists gamma comma delta belongs to Z of I such that P is equal to gamma into delta, then P square is equal to n of P, which is equal to n of gamma into delta, which is equal to n of gamma into n of delta. So, consequently, n of gamma belongs to 1 or P square. We claim that n of gamma is not equal to P. On the contrary, assume that gamma equal to A plus IB and P equal to n of gamma, which is equal to A square plus B square, A square plus B square. Then clearly A and B are different parity, and hence A square plus B square is not equal to 1 mod 4, which is not congruent to 3 mod 4, which is equal to P. Thus, n of gamma is either 1 or P square. Hence, either gamma or beta is a unit in Z of I. So, now we are going to prove the third part, that is, if P is congruent to 1 mod 4, then we know that minus 1 is a quadratic residue modulo P, that is minus 1 by P is equal to 1. So, that is equivalent to say that there exists an x naught belongs to 1 to 3 up to P minus 1 such that x naught square is congruent to minus 1 modulo P. So, now we consider the set S equal to A plus B x naught belongs to Z, where A is lies between 0 to root P and B is lies between 0 to root of integer, greatest integer value of root P. Then mod of S is equal to greatest integer of root P plus 1 whole square, which is greater than P, has greatest integer function root P is equal to root P minus u for some u belongs to, for some u and where u is strictly lies between 0 and 1, and therefore, root P integer function plus 1 whole square is equal to root P plus 1 minus u whole square, which is greater than root P whole square, which is equal to P. So, as S has more than P elements and each of them leave remainder 0, 1, 2, 3, P minus 1, exactly P in number, when divided by P, there will be at least 2 numbers for which the remainder will be the same. That is, there exists A1, B1, A2, B2 belongs to 0 to greatest integer function of root P such that A1 plus x naught B1 not equal to A2 plus x naught B2, and A1 plus x naught B1 is congruent to A2 plus x naught B2 mod P, or equivalently A1 minus A2 is congruent to x naught into B2 minus B1 modulo P. So, let us take A equal to modulus of A1 minus A2 and B equal to modulus of B2 minus B1, then minus B square is equal to minus 1 into B square, which is congruent to x naught square into B square, which is x naught B whole square or A square modulo P. Thus, we have A square plus B square is equal to Kp for some k belongs to n. Moreover, 1 is less than or equal to A comma B is less than root T gives us that A square plus B square is less than 2p, hence k equal to 1 is the only possibility. So, we have that A square plus B square is equal to P, that is, we have shown that whenever P is congruent to 1 mod 4, then there exist integers A and B such that P equal to A square plus B square, which is equal to a plus ib into a minus ib. The rest of the part is also follows as a is not equal to plus or minus b. In this module, we defined Gaussian integers and saw various properties of Gaussian integers. We defined primes and composites in Gaussian integers. We observed that the primes which are in integers are no longer primes in Gaussian integers. As in first example, we saw that 2 is no longer prime, is a no longer Gaussian prime, and also we observed that the primes of the form 4k plus 1 are going to split in Gaussian integers, whereas the primes of the form 4k plus 3 are going to retain as primes in Gaussian integers. That means they are inert as in the Gaussian integers as well. So, now the ring of Gaussian integers is an example of ring of integers in the extension field of rational numbers. There are other sets of rings of integers in other extension field of rational numbers. An interested reader can refer any standard textbook of algebraic number theory. With this, we end this module.